Okay, hello. This is tutorial that covers Caesar cipher breaking material, and what we will do, we'll consider Caesar cipher breaking procedure, and we'll try to implement it in Octave. Actually, I'm already attaching you to the announcement post the already Caesar.m file. That's the script that you can execute in Octave. But I would like to elaborate more on how it works and how it can be improved, and mainly important, how can we improve it to address more sophisticated problem, which is breaking of the visionary cipher. We'll talk about visionary later on, but as of now, let me just briefly address the environment that we have here. And okay, not what I need. Here it is. So I do have the Caesar.m file open in an editor on my local machine. So I'm working on Mac, but it's not important. On the previous tutorial, I showed you the way how you can transfer files back and forth between two machines, between your workstation and our Octave server. So you can use, for example, FileZilla to do this. But I also mentioned that if you work on Windows 10, you can execute Linux environment, particularly Bash environment, from within Windows. And in this case, you will be very close to the environment that I'm working on. So think of this. There is an editor with a text file opened. This editor we'll use just to write our script, our MATLAB script, or actually Octave script. And I also have a Bash session, similar to what you can organize on Windows. My script file is saved here. The file is called Caesar.m. I also have another file nearby. It's called sftp.batch. This file is here. Its simple content is just one line, put Caesar.m. This is the command for SFTP client, for the command line version of the SFTP client that will execute every time we'll make an update to the Caesar.m. Of course, there exist more sophisticated and more convenient options of how we can edit a file directly hosted on the remote server, but assuming that you work mainly in Windows environment, not all of these solutions will work for you smoothly. This solution will work without any issues, and I'm pretty sure you will not face any technical problems with that. So let me illustrate how it works. That's the file on my local machine. And I'm switching to the command shell, to the shell environment. And I want to execute a simple command. FTP-b, FTP-batch, so that's the name of the file, -b, that's the command line option that allows me to specify that file as the batch. Batch in this sense is considered to be sequence of SFTP command. And the only SFTP command that I'm going to execute is to put Caesar.m. And now I want to specify the host that I want to send this file to. And it would be Simon Bayev, octave.wcm.net. Of course, in your case, username will be different, but the rest will be the same. Should I hit enter? That's it. The file Caesar.m got sent to the Octave server, and now it can be found in the Octave. Let me quit my Octave session and show you that here is the file. Let me even remove it from my home directory on the Octave server. Now I don't have this file stored in the home directory. And if I go back to my shell on the local computer and re-execute this command, and we'll go back to Octave server, here it is, cipher.m. How can I execute this file? I want to start Octave first. I type in Octave. I want to clean up the screen by Control L and just type in the name of the script file, which is teaser. That's it. So the file got loaded. If it has no syntax error, it will not show you any error messages like in my case. And you can confirm that the file was successfully loaded by executing whos command. And there should be two variables, alpha and gram. We'll talk about them in a moment, but let us now switch to the set of PDF slides that I'm sharing with you that outline the scissor breaking procedure. So first of all, the scissor breaking, the scissor cipher by itself belongs to the class of symmetric cryptography or classical cryptography. It means that the same key is used to encrypt data and decrypt data. Any crypto system, not necessarily classic crypto systems, can be considered as described from the quintuple of 5 terms. Set of plain text, in other words, the message that you want to encrypt. Set of keys, so those are encryption keys. Set of ciphertext, that is the result of encryption. And the two procedures, encryption and decryption. In case of symmetric cipher, the same key is used for encryption and decryption. In case of asymmetric cipher, also known as public key cryptography, the set of keys would contain a key for encrypt data and another key for decrypt data. Those keys will be linked one to another, but will not be the same. Scissor cipher, as I said, is a symmetric cipher, and particularly binding the scissor cipher to the definition of a crypto system, we can identify that M, which is the message or set of plain text, would be just a sequence of letters in Roman alphabet or in English alphabet, if you wish. The K, which is the key, it is just an integer in the range from 0 to 25. That range of integer value is identified after the length of the alphabet. So particularly English alphabet contains 26 letters. That's why the encryption or decryption key, an integer, would contain an index of those letters. So in other words, instead of a number, we could say my encryption key is letter A. A numerical value associated with letter A would be 0. Or I can say my encryption key is letter Z. Letter Z would correspond to the number 25, integer number 25. Encryption procedure is to add index of one of the letters in the plain text message to the number that represents the key. So for example, if I want to encrypt letter D with key of 3, letter D contains the index of 3 because A is 0, B is 1, C is 2, D is 3. So if my letter in the plain text message, just one letter out of many, the first one, is letter D, and the key is 3, result would be 3 plus 3, which is 6. Modular arithmetics can be considered in this context as a remainder of division. So remainder of division of 6 by 26, it is still 6. So in this case, result of encryption would be 6. In other words, letter D encrypted with the key of 3 results in a letter that has index 6 in the alphabet. And let me scroll a couple slides advance to show you. Okay, not this one. To show you the alphabet. You know that the alphabet spans from A to Z, since A is 0, 0, 1, 2, 3, 4, 5, 6. So a letter with index 6 would be G. In other words, D in the plain text message becomes G in the ciphertext. That's how encryption works. To decrypt a CIS cipher, you want to pretty much subtract the value of the key from the resulting index of the ciphertext letter. So if I want to decrypt letter G with the key of 3, I would need to identify that G is associated with the numerical number 6. 6 minus K, which is 3, gives us 3. And then you have to add 26. This operation, addition of 26 in the decryption procedure, is required to avoid negative numbers. Negative numbers can easily be seen if, for example, K, absolute value of K, is greater than absolute value of C. So what if you have to decrypt with an integer key of 26 or 25? So C could be something like 5. 5 minus 25 is negative 20. So negative 20 modulo 26. Modulo operation is defined on negative numbers. But as I said, in the context of our problem, modulo operation has to be treated as the remainder of division. Remainder of division is not well defined for negative numbers because it's hard to say what will be the remainder of division of negative 20 by 26. We actually can make some guesses, but it's not the scope of our discussion. But we also know that adding up the number to the left-hand side of the modulo operation that matches the right-hand side doesn't change the result of the modulo. So if you doubt about this equality, you can say that 2 p.m. and 2 a.m. are the same modulo 12. If you not use a.m. and p.m. notation for the time, you could say 2 at night is equal to 14 modulo 12, something like that. So that is the decryption operation, and the set of the ciphertext letters is matching the set of the plain text letters, which is just an English alphabet. Okay. Now this set of slides present a few attacks to the well-known ciphers, and pretty much you want to learn the basics, but of course there is a lot beyond this separation of 3 attacks, because this is just a rough separation to introduce ciphertext only attack. That is actually what we're going to do with the CIS cipher. The idea is that the adversary, the attacker, is considered to intercept on the ciphertext, but she doesn't know the key and she doesn't know the plain text. She will guess the key and the plain text based on the ciphertext. For the cipher like Caesar, it is pretty easily doable, but for other ciphers, it's not that easily doable, especially if those ciphers are complicated. Known plaintext attack assumes that not only a ciphertext is known to the attacker, but also a set of pairs between a ciphertext and the plaintext. Not necessarily, actually, not the plaintext that is associated to the ciphertext in question, but some other pairs. For example, I am getting some ciphertext, but I know that with that same cipher, word hello corresponds to the text core, or some other text with the same number of letters, but with different letters. So that would be known, that would be called known plaintext. Because having those pairs that associate some ciphertext with some plaintext, assuming that ciphertext and plaintext are linked through the same key that is used now, we actually can decipher the key, and then knowing the key, we can figure out the plaintext. The plaintext that is that matches the given ciphertext. And the last attack is probably, I wouldn't say the easiest, but the one that has the greater chances to be broken, to be not attacked, but to be successfully implemented, let me say this, is the choosing plaintext attack. The idea is that not only an attacker has a finite set of pairs between ciphertext and plaintext, but also an attacker is assumed to be able to use some kind of engine, encryption engine, that is fed with the same encryption key. And then, for example, I'm sending some text, and it gives me the associated ciphertext. Again, I'm already given with the ciphertext that I want to break, and I don't know what plaintext is associated to that ciphertext, but I can send some other plaintext, and I will get the ciphertext. Of course, if I know that the set of messages to be sent is limited, I can just send each and every possible plaintext message to that engine. We'll get corresponding ciphertext, and if the set of messages is limited, then one of the ciphertexts will match the one that I'm given with. So associated plaintext will be the one that I'm interested in finding. And finding of the key in this context is pretty much a sub-problem to the finding of the key is known plaintext, simply because the set of pairs between ciphertext and plaintext now is unlimited. I can get as many pairs as I want. So we're going to skip few slides and actually scroll all the way to the breaking of the CIS cipher. So CIS cipher not only is known to be a symmetric cipher, but is also known to be a substitution cipher. Substitution cipher, the general idea of substitution cipher is that it doesn't change the structure of the text. It only changes, substitutes one letter to another, but structure of the text in terms of number of letters or the alphabet is still the same. And in our case, CIS cipher perfectly meets the requirement of the substitution cipher, because the way it works, it just substitutes one letter of the alphabet to another letter of the same alphabet. And let us now consider an example of using CIS cipher, which is to encrypt hello world. So when we encrypt hello world with the key of 3, so that is some arbitrary key that was chosen by the author of these slides, and the result in ciphertext would be coarse rock. It is important in this example that our alphabet is composed only from characters from A to Z. There are 26 letters. Here in this plain text, you also see a space. A space is a character, but we don't have this space character in the alphabet. That's why before we can apply scissor breaking procedure, we actually have to consider eliminating of all characters that are not listed in the alphabet. In this example, space from the plain text is preserved to the space in the ciphertext, but that is done only for the convenience and for the sake of illustration. A real problem example that we will deal with would contain just 10 letters, horse rock without any space between them. And we would recover hello world without a space in between these two words. That is important. Later on, when you will deal with visionary cipher with extended alphabet potentially, you can say that space is one of the letters or one of the members in my alphabet. And in this case, you can actually stick with pretty straightforward conversion of any normal English text into the ciphertext. So spaces, commas, everything else will be preserved. But as of now, our alphabet is pretty limited. It only contains 26 characters and no space. So I hope you can see clearly how H becomes K, E becomes H, L becomes O. We just add 3 more positions towards the end of the alphabet. So H plus 3 position, A, B, C, D, F, A, H, G, wait, A, B, C, D, E, F, G, H, I, J, K. So between H and K, there are 2 letters I and J, but if you want to transit from H to K, you have to shift 3 times. So H with the key of 3 becomes K. How do we attack the cipher? And you probably can see this very clearly, that there is a possibility for exhaustive search. Exhaustive search simply assumes that what if we are given with the ciphertext, again, only ciphertext, we don't know the plain text ahead of time. And we assume that encryption was made with the key of 0, first of all. So we decrypt the ciphertext using the key of 0, and we recover some plain text. With the key of 0, plain text, recovered plain text would be exactly the same, horse rock. And then we use our ability, our knowledge of the language to identify the fact that the plain text is actually English or not English fragment. So horse rock is obviously not an English fragment, and we move on for the key equal to 1. With the key equal to 1, horse rock will become something else. So K would become J, H would become something else, etc., etc. And then horse rock will render in some ciphered, in some plain text candidate. And again, we want to look at this plain text recovery and decide whether or not it is English. In this case, we'll have to apply this same operation 26 times. Luckily for us, since the correct key was 3, the 4th time we will be applying this operation, we will resolve horse rock into hello world. And we can clearly see that hello world is in English, so that's why everything is correct and the key was 3. The biggest issue with this approach is that not because that you have to potentially try 26 combinations. 26 combinations if the length of alphabet is 26. If length of alphabet would be 100 characters, then you will need to try 100 combinations. But from the standpoint of computing, trying 100 combinations is not a big deal. The biggest issue here is that to identify correctness of any reconstruction, you really have to use your own, your personal, your human ability to look at the ciphertext, or to look at the result of the recovery and say whether or not it is an English fragment. In other words, it is not an algorithm. It is just a helper that gives you a bunch of reconstruction attempts, and you want to look at them and then say, okay, that is English. If it is English, then that is the matching key. So we cannot accept this option mainly because we are targeting to develop an algorithm that will tell, okay, with very high probability, the key was that, and this is your plain text. Can you confirm that it is English? If you confirm, then yes, you don't need to try anything else. You just confirm the fact that the break-in procedure was successful. So in other words, instead of having 26 conclusions, like in this case, with 26 conclusions, you will have only one positive outcome and 25 negative outcomes. The algorithm that we are trying to manage, it is just one candidate that we want to say, that we want to analyze. Is it positive or negative? Okay. If the outcome is negative, then something wrong either with our break-in procedure or with some other reasons that you will see in a moment, or maybe it wasn't even a Caesar cipher. Okay. So the key point in this break-in procedure, automated break-in procedure, is something called 1-gram model of English. 1-gram model of English, it's nothing more but a statistical data, set of statistical data that shows how frequently each individual letter in English alphabet appears. And we can say that letter E in English language is the most frequent letter. And then probably the next one would be letter O, if I'm not mistaken. Actually, letter T. I could have missed something, but okay, T has the 090, and then we have a bunch of 080, and then 070, etc., etc. But in other words, E is the most frequent letter, and then, for example, Z is the least frequent letter, and all other letters somewhere in between the two. Okay, so the main part of the is actually look at the given ciphertext, which is horse rock, and identify statistics for each possible letter in this ciphertext. So here in our case, we have how many? Have seven individual letters, 7 non-repeating letters. K, H, O, R, Z, U, G. There are 7 letters. Those letters of the alphabet that do not appear in this ciphertext can be considered as having 0 value associated with them. Talking about these values, we can just count how many times character G appears. So, for example, character G appears only once, and the number of letters is 11. That's why it has the frequency of 0.1. Character H also appears once, but character O appears 3 times. 3 times divided by 10, it's 0.3. Character R appears 2 times. So there's frequency. All other letters have the frequency of zeros. And now if you consider the original English frequency table and the table that you have just compiled, you would say, okay, my ciphertext table doesn't match the table that is associated with English. So that is numerical measure of the fact that you are not dealing with English. So pretty much you just need to compare the two tables. Now, how the algorithm works. The algorithm still will require you to try all 26 possible keys. For all 26 possible keys, you have to calculate the shifted version of this representation. So for example, when you try a key of 1, instead of G, you would have F. And then instead of H, you would have G. Instead of K, you would have J. So in other words, with the same numbers, you would have different labels. Again, 0.1, this 0.1, will now be associated with letter F. That 0.3 that was previously associated with O will now be associated with letter N. And result of this operation would be different table. Different table that also has to be compared with English. How many tables we can compile? 26 possible tables. 26 possible tables, and each of these tables has to be compared with the English table. The only question is, how do we compare the two tables? And how can we say that one table is closest to the English table? Because there will be only one table that closest to the English, and that is the table that is associated with the key that was the correct key. There is one issue that we'll see in a moment, but let me just sound that issue. Our tables are only partially defined. So instead of having 26 different numbers, we have 7 non-zero values and other values of zeros. So other labels are associated with zeros. So 26 total, 7 non-zeros. It means that there will be 19 zeros in each possible table. When we will be comparing tables, of course, we will never have the exact match. So we are talking about a table that will be the closest, excuse me, the closest to this table. So if you scroll further, you will see actually the solution to the problem of how tables can be compared. The general idea is actually calculate a correlation function with every given pair. Actually, not just with every given pair, but with English table on one hand and one of the 26 tables on another hand. So in other words, we want to define a correlation function and calculate, which is phi of I, and then calculate that correlation function for each and every table tables will be referenced with some value of I, which in fact is the same as the value of the key. As we have 26 different tables, we have 26 possible keys. So we can say that every table is associated with one particular value of the key. So the correlation function, the function itself, is fixed, but we will have 26 different values of that function. And values of the function, by the way, this is the function. Values of the function will depend on individual frequencies in 1 gram, individual frequencies in the ciphertext. And they will also depend on frequencies listed in 1 gram table. And they will also depend in the particular value of the key. Okay. Now, as we have only 7 non-zero labels, our correlation function, instead of having 26 different terms, summation of 26 products, it will have only 7 terms, summation of 7 products. And summation of the 7 products is expanded here. So f of c, that's the frequency of a letter in the ciphertext. And we know that those frequencies are 0.1, 0.1, 0.1, 0.3, 0.2, 0.1, 0.1. Look at this. 0.1, 0.1, 0.1, 0.3, 0.2, 0.1, 0.1. So these are just in sequence sorted with respect to the appearance of letters in the alphabet. What are these entities? P of 6 minus I. P of something is actually a value in 1 gram table. It is not letter P here. That is just entry in the table. And 6 minus I is the index in that table. What is that 6? The 6 is the index of letter associated with that weight. We know that our frequencies are G, H, K, O, R, U, and Z. So the very first one with the frequency of 0.1 is associated with letter G. And letter G in this table, 0, 1, 2, 3, 4, 5, 6, has the index of 6. Here it is, that's 6. And then the next letter was H. H is associated with the weight of 0.1 and 0.1 here. And letter H is the next after G, so it has the index of 7. That's why it is 7 here. Value of I is actually our effort to shift the table. So instead of shifting this sequence, as I mentioned before, when I said that G would become F or H would become G, etc., etc., we can actually shift the original table. There are many ways of how correlation function can be defined. In this particular case, we take a value in 1 gram table and shift it I position to the left. So 6 minus I defines index in the 1 gram table corresponding to encryption key of I. When we try encryption key of I, equal to 0, for example, it would be 0.1 times p of 6. 0.1 times p of 6, and p of 6 is that. So you just substitute 0, 0, 15 instead of the first term, and then you would substitute 0.1 multiplied by 0, 0, 60 in place of the second term, and so on and so forth. Then you calculate the summation, and that would be your phi of 0. By the way, phi of 0 is that. Then you apply exact same procedure with I equal to 1. So for example, when I equals to 1, p of 6 minus 1 would be p of 5. P of 5 is 0, 1, 2, 3, 4, 5, would be this. So your first term would be 0.1 times p of 5, and p of 5 is this. And then you calculate everything with I equal to 1, and that is your phi of 1. It's supposed to be this value. Okay? Because of the fact of how correlation function is composed, actually it can be proven. The maximum value of the correlation function will correspond to the case when we are considering the closest possible table to the 1 gram table. So in other words, when we consider a correct key, a correct value of I, the value of the correlation function will be the maximum. So we just need to look at all these numbers and find out the one that is the biggest. And if you look at the results, the biggest phi of I is 0.060, 0.660, and it corresponds to the value of I equals to 6. That is the biggest value. And what do you think will be the plain text? You built Lola, not hello world, but this one. So it actually doesn't work the way we expected. The only reason for that is the length of the ciphertext. The main reason that it doesn't work is the fact that instead of having the fully defined table of 26 entries, we have only 7 entries defined, and 19 entries are undefined. In other words, we're saying that our ciphertext belongs to some alphabet where only 7 letters are in use. All other letters are never seen in any text. That is incorrect. That's why such a method, such a breaking procedure that we are considering, is not a guarantee of the result. In fact, only the third reconstruction attempt, so correct value of phi of I, it's the third winner from the top with the I of 3 and with the correct reconstruction value. But as I mentioned before, our breaking procedure simply assumes that we apply the method and it gives us just one result. In other words, our expectation would be to use this plain text reconstruction. So we will take a look at this. We'll say that's not English. So we mark our experience as failed. Now we want to identify the reasons of failure, because we're not going to consider these results. We just consider the very first winner. It is not English, method failed. That's it. We know why it failed, because the ciphertext was short. And you will see in our Octave demonstration that if instead of hello world we encrypt something longer, you will get a very decent quality of the recovery. But with the hello world, with only 7 unique letters out of 26, pretty much you have no chance for the correct reconstruction. Okay, so now let us implement this procedure in Octave. And that is the program. I'm going to comment it, each and every statement of this program. And I believe the other tutorial works you through the creation of this program. But let me just start from the very beginning. First of all, we define the alphabet. The alphabet is the sequence of letters from A to Z. From the standpoint of defining a sequence, we actually are defining a vector. A vector of characters, or a matrix of characters in Octave, is a text. And let me just do a simple demonstration of this idea. So, for example, if we want to consider a sequence of numbers 1 to 7, it is an array or it is a vector. If we assigned it to a variable a, then length of a would be 7, and a is actually a matrix 1 times 7. If we consider a sequence of letters from A to D, small letters, that is A, B, C, D, and if we assigned it to variable s, length of s would be 4. So we introduced actually an array of characters, which is a 2-dimensional array shaped as a single-dimensional vector. Now, if we define S1 being A, B, C, D, and we already have S, do you think that they are the same? From the standpoint of Octave, they are the same. A string and an array of characters. These are two same things, and you can actually look at this by subtracting S from S1. We got all zeros in 4 different places, in 4 possible positions. It means that S and S1 have exact match. From the standpoint of comparing two strings, of course, we can use something like strcmp, if I'm not mistaken. That's the function that exists in any programming language in some form. And the answer is true. It is not true, it is 1, but 1 is true. If I, for example, compare SD with FG, result would be 0. So comparing n and S1 is 1 that is true. But we can also implement another more granular comparison of two strings. You should remember from my previous tutorial that there is a function called find, and function find can be fed with an array of entries, and it returns indices of all non-zero elements. So if we feed it with a result of S minus S1, in other words, if we feed it with this array, then obviously it cannot find any non-zero values, but the important thing is that if we apply length of this, then we simply consider that there are no non-zero elements. If there are no non-zero elements, means all elements are zero. Zeros means S is identical to S1. If instead we define S, for example, as like B to E, instead of A, B, C, D, we defined it as B, C, D, E. And we apply our evaluation, we will say length is 4. It simply means that S minus S1 are all ones, because S is this, 1 is that. In two different strings, individual characters do not match. And pretty obviously, if we compare it using strcmp command or function, the result will be 0, which is false. Okay. Now, the variable alpha that we have defined in that script is actually a sequence of letters from A to Z, and the length of alpha is 26. 26 characters in the string, and it is the same as an array of characters of length 26. Now, what is gram? Pretty obviously, gram is a vector that corresponds to one gram table from our slides. And is the one? No, it's not the one. That's the one. We don't have letters in that table, and let me put them side by side. So 080, B would be 015, then C 030, D 040, and so on and so forth. Z would be 002. So it is shaped from A this way, and here it is just one big line. So now let me show you what the gram table is in our Octave session. It is gram variable, and that is how it's defined. Okay. What's next? Next we have a function called clean. Function clean is needed actually to remove all letters from the text that we want to process. We want to remove those letters that do not belong to our alphabet. And let me show you how it works. So not only it removes a space and exclamation marks, but also it applies conversion of characters from lowercase to uppercase. We actually have to say that implementation of the clean function should be a bit different because character E in that text is not listed in the alphabet. So it is about to be removed. But we assume that character E and character E small and character E capital, they are the same. And since our alphabet contains only capitalized characters, we want to convert small letters into capitals. That's why application of this function returns us hello world. Okay. The way how it works, first of all, this is a function. Any function in Octave is defined in such a way that you declare a returning variable. So it's, instead of using a return paradigm or return statement methodology, we just define a variable, it could be anything, that will be assigned during the function execution. So somewhere in the body of the function, we have to assign that variable. And the fact that I'm using the variable result, it actually means nothing, but just one of the variable name. So variable name result will be used to actually return the result of the cleaning. The function itself is called clean. It gets two parameters, s and alpha. S is assumed to be the text that we want to clean. Alpha is assumed to be the alphabet. Despite of the fact that alpha is already defined in that script, we cannot say that this function and that definition of alpha belong to the same entity. So this set of functions and these two variables, alpha and gram, are totally independent. It is not a definition of the class. It is just definition of multiple independent objects. That's why in the body of this function, we cannot use alpha without explicitly passing it to the function parameter. That's how we use it here. We know that alpha is now available in our Octave workspace, and we pass it as the parameter to the clean function. So using the terminology, programming language terminology, alpha here would be actual parameter, while alpha here would be the formal parameter. Now, we use several functions. One of them is toUpper. Let us see how it works. You probably can guess that hello 1, 2, 3 passed to this function would return hello 1, 2, 3. So in other words, it applies uppercase into all alphabetic characters, and it doesn't touch anything else. If there is a space, it wouldn't touch a space. It only converts alphabetic characters. Now, let me make it. Now we have a function called strcat. Strcat is the function that can be used to concatenate multiple characters, and the reason that quotation marks are highlighted probably because it would be more satisfied with single quotation marks and use. Okay, by the way, when we make any change to the cipher.m, remember that this is the editor that deals with a local file in my system. Now I made some change, I saved the change, and now I want to transfer this change to my Octave server. So I go back to my shell and I repeat my transfer command. Now it's been transferred. And now I want to execute Caesar statement again to reload the script. How do I know it is reloaded? I just know this. If you're wondering if it will continue to work, I can just execute clean hello world. It will execute. And actually, I can quit the Octave session and display the content of the function Caesar. That's my latest change. Okay. So now, when you need to make any change, I will just do the change without providing any comments to this. I'm starting Octave. I'm loading Caesar, and let us see what else we use here. So to uppercase is the function that is applied over the given text. That is the first argument of the function that is called on the outer scope, and that function is called regexp replacement or regexp rep. So pretty much this function takes its first argument and finds any match to this regular expression and replace it with empty line. Replace it with an empty line. I need to make a small pause. Excuse me for a second. All right. So, and the regular expression that we deal with is comprised from 3 parts. This is the one part, our alphabet is another part, and this is the third part. Pretty much, we just define a character class that is not listed in our alphabet. So this entire thing is equivalent to regex replace. Let me just say hello world with exclamation marks, and then my regular expression would be A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. And I replace it by, it looks like I made a mistake because I've forgotten to use to upper to the given text. Now it is hello world. That's how it works. And then we have a few more functions, encryption, frequency, breaking. I probably want to comment them on the later session because it will be more appropriate to do so when more listeners will be here during the active session. So I will combine this material with the material that I will present for the visionary cipher, and in this case we'll have just a discussion over the functions that we want to use from the Octave standpoint from the Octave standpoint to break both Caesar and then the generic cipher. All right. So if you're wondering how these functions work, I encourage you to watch the other video tutorial from the previous years that I posted, and I believe there is a discussion about these functions on there. And if you have any questions, just ask them on the discussion board. I will be more than happy to answer them. That's pretty much it for today. And I will make an announcement about our next tutorial. Probably it will happen later this week. So thank you for watching.